Welcome to today's deep dive. Imagine a liquid that doesn't boil and, doesn't evaporate, but instead it spontaneously climbs up the walls of its container.
Yeah, it literally slips through these microscopic atomic scale cracks and just flows with absolutely zero friction.
Right. I mean, it looks like it's straight up defying gravity, but it's actually doing something, well, much more profound.
It really is. I mean, it's revealing that our macroscopic rules of physics are just surface level. When you drop the temperature of a liquid near absolute zero, it turns gravity and really the very fabric of reality into an experimental question.
Okay, so let's unpack how a liquid actually breaks the rules of friction, because we're looking at helium here, right?
Exactly. Mostly helium-4 and helium-3.
Right, and helium-4 is famous for forming those like creepy wall-climbing thin films. But with helium-3, to reach this frictionless state, the atoms actually have to pair up. Why the difference?
Well, it comes down to the underlying quantum mechanics. You see, helium-4 atoms naturally behave like particles that can easily share the exact same quantum state.
Okay.
But helium-3 atoms are fiercely individualistic. The laws of physics actually forbid them from occupying the same state.
So how do they become a superfluid then?
They have to bond into pairs.
Yeah.
Once paired, they bypass that restriction and suddenly behave as a single unified collective.
Okay, so instead of my usual analogy of, a chaotic crowd bumping into each other to create friction,
Right?
it's not just that the crowd links arms to move together, it's that everyone in the crowd literally loses their individual identity.
Exactly.
They occupy the exact same space and state, moving perfectly as one single entity, no bumping, no resistance. So it's not anti-gravity, it's just the end of our everyday intuition.
Precisely. It's a macroscopic quantum state. And because the fluid is acting as one unified quantum entity, it stops behaving like messy water and starts following pure fundamental mathematics.
Which is wild.
It is, and this is where it becomes a laboratory model for the cosmos. We can use it to mathematically mirror massive cosmic events, like the aftermath of the Big Bang.
Wait, let me push back on that for a second. I get that the math is similar, but how exactly does cooling a beaker of helium simulate the literal expansion of the universe?
That is a fair question.
I mean, they're completely different scales and materials.
Yeah, but it's all about phase transitions. During the Big Bang, as the superhot early universe cooled down, the underlying vacuum transitioned into having physical structure.
Okay, I'm following.
And this process occasionally created topological defects. Think of them as essentially permanent scars in spacetime where the new structural rules just didn't quite line up.
Ah, like a glitch in the ice when water freezes.
Great analogy. When physicists cool a superfluid in a lab, it undergoes an identical mathematical phase transition. The liquid suddenly snaps into its highly ordered quantum state.
Wow, and we can physically watch those exact same scars or structural defects form in the liquid.
Yes, exactly. We're essentially watching a vacuum become physical.
Okay, so if we can model the early universe's phase transitions, we can model other extreme phenomena too, right?
Oh, definitely. Think about what happens when you stir a glass of normal water.
You get a whirlpool that eventually just dies out because of friction.
Right, but stir a superfluid and you create what we call quantum vortices. Because the fluid state is quantized, these vortices exist in fixed, discrete steps.
Wait, so you don't get a messy fading whirlpool?
Nope. You get a perfectly stable structural pillar of rotation. And this forms the basis of a field called analog gravity.
Analog gravity. So
Yeah.
they use these spinning vortices to simulate how waves behave in curved space.
Exactly. And this is exactly how they simulate a black hole's event horizon.
That is incredible because sound waves in the superfluid travel at a specific speed, right?
Yes. So if the fluid is swirling around the vortex faster than the speed of sound, those sound waves get entirely trapped.
Oh, wow. They can't escape the flow moving backward, exactly like light trapped past a cosmic event horizon.
Precisely. And since we obviously can't take a ruler and sensors up to a real black hole, these superfluids let scientists test the complex math of cosmic event horizons right on a laboratory desk.
That is such a huge deal. It lets us measure the impossible.
It really does. Superfluids prove that matter operates by completely different rules under extreme conditions.
So next time you pour a glass of water, just remember that friction, resistance, and, the way liquids splash, those aren't permanent, unbreakable laws for you or the universe. They are literally just the default settings for our warm reality.
And I'd consider this final thought to mull over.
Yeah, let's hear it.
If a seemingly simple liquid like helium is actually hiding a deeply complex collective quantum state that only reveals itself near absolute zero?
Okay.
What if the empty vacuum of space-time itself isn't just an empty stage? What if the fabric of our universe is actually a deeply complex quantum fluid, and we just haven't figured out how to see it yet?